Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 16. Today we'll be constructing perpendiculars. If I asked you the distance from you to the wall in the room that's furthest away from you, what would you estimate that distance to be? Did you connect straight from you to the wall? Did you take a roundabout way? What is the shortest distance from a point to a line? Well, Euclid figured this one out too, and it has many practical applications in life. If you are on a farm and you want to connect a hose to the faucet to water a line of trees, or maybe you are an engineer and you want to connect high-speed internet cable from a house to the main cable, how do you know how much hose or cable you need? Don't you want the shortest amount? Let's look at this first investigation. We want to find the right line. So we've already constructed a perpendicular bisector of a segment. But what if I have a line and it's infinitely long and we can't bisect it? How can we look at it? So we're going to draw a line and a point not on the line and label it P. What if we use the converse of the perpendicular bisector theorem? So draw points A and B on the line that are equidistant from P. Does that give a meaning to where P is located? It should be on the perpendicular bisector. So now construct the perpendicular bisector of segment AB, and point P should be on it. Label the intersection that you make point M. You have now constructed a perpendicular from point P to the given line. This is useful in finding distance to a line. But let's look at that some more. We're going to draw 3 more points on our line AB, Q, R, and S. Compare the lengths of PQ, PR, PS, and PM. What is the shortest distance from a point P to the given line? Okay, here's this investigation on video. We're going to draw a line AB, and then we're going to label a point not on the line as P. Now, if we want to find 2 points on the line that are equidistant from P, we can just set our compass up and just draw 2 points that are the same distance away. So remember, when you go to one side and the other of the line, you want to keep your compass at the same position. Now I'm going to label those points A and B. They are equidistant from P. If I want to construct the perpendicular bisegment, the perpendicular bisector of segment AB, I'm going to need 1 more point on the other side of the line to connect to P. So again, equidistant, I'm going to overlap my arcs from A and B that are equidistant away. And now I have a second point that's on the perpendicular bisector. Any 2 points I can draw a straight line in between. So that straight line is the perpendicular bisector. I'm going to label that intersection point as M. Now I'm going to draw 3 more points on the line just to test some things out. I'm going to want to be measuring these distances to these different points. I already know that A and B are equidistant away from P, but I'm going to label these other points Q, R, and S. And then I'm going to measure the distance between P and Q, P and R, and P and S. And I'm also going to measure the distance between P and M, M being on our perpendicular bisector. Because these are short distances, I'm going to go ahead and use centimeters. So what point is the shortest distance from P to the line? Right there, the one on our perpendicular bisector. So our shortest distance conjecture is the shortest distance from a point to a line is measured along the perpendicular bisector from the point to the line. So the shortest distance is going to be perpendicular to the line or the wall or the line of hose that you're trying to get to. Let's look at this on patty paper. So on a piece of patty paper or tracing paper that you can see through, draw a line AB and point P. Remember that P is not on the line. Fold that line onto itself and slide the layers of paper so that point P appears to be on the crease. Crease it and unfold it. Is that crease perpendicular to the line? You can check it with the corner of a piece of paper or your protractor. Label the point of intersection M. Are angles AMP and BMP congruent? Are they supplementary? Why or why not? In this second investigation, M, is it the midpoint of AB? Do you think it needs to be? Think about the techniques we've used in these two investigations. How did they differ and how are they the same? Let's look at this investigation on video. This is a piece of paper that can be seen through. We're drawing a line and we're putting A and B on it. Now when I put point P up here, it's not necessarily equidistance between A and B. So I'm going to fold my paper. And before we had done a midpoint, and so we overlapped A and B, but this time P needs to be on the crease. So scoot it over so that P is on your crease and that you're lining up the line on the top and the bottom. So make sure that they're on top of each other. They coincide. And P is on the crease. P is on the crease and the lines are on top of each other. Unfold that. And you might want to draw a line in your crease so you can see it better. Compare the angles after you label M. I used a protractor to measure my angles. And since P is right at 90, I know that AMP and BMP are 90 degrees. So they are congruent. And 90 and 90 is going to add up to 180, so they are supplementary. Now I'm going to measure the distance AM and MB. So M is not the midpoint here. But is that necessary? Is the line PM still the shortest distance from P to line AB? So why do we need shortest distances or perpendiculars? Where else do we use them? Well, we use them in altitudes. So an altitude of a triangle is a perpendicular segment from a vertex to the opposite side or to a line containing the opposite side. So sometimes it can't always be on the opposite side. Let's look at this triangle. It's a perpendicular segment from a vertex to the opposite line. So this line, and now I'm going to want perpendicular. So in this case, it comes straight up, and so that forms a 90-degree angle. But what about from this line to the vertex? It's not going to be in the middle like this one was. It's going to be roughly here. Again, this is 90 degrees. So this is one altitude of the triangle. This is a second altitude of the triangle. Is there another altitude? There is. We have the last vertex over here, and we're going to draw perpendicular. So our last altitude is over here. On every triangle, we're going to have 3 different altitudes. Now, all of these were inside the triangle because this is an acute triangle. So an altitude can be inside the triangle, but an altitude could also be outside the triangle. So this is an obtuse angle, and when we go to draw the altitude from this vertex to this line, we can't get 90 degrees unless we extend that line out. And so the altitude actually runs outside the triangle. And then on a 90-degree triangle, the altitude from this vertex to this line is going to be the side of the triangle. And the same thing from this vertex to this line, also the side of the triangle.